Hi everybody, welcome to another video in Calculus 2, section 10.3, Infinite Series. So in the previous section we studied about a sequence, and the sequence is convergent or divergent. This time we study about series. So sequence is individual terms, whereas series is a sum, so a sum of infinite terms. Right. Now, just go over some terminology first. And we say, suppose the series is convergent. Having a constant, we can take that constant outside. Does that sound familiar? Yes, it is in summation, it is in derivative, it is in integral. And of course, here's the summation. Right. Next, if it is divergence, then when you multiply a number to it, it still diverges. If that is the non-zero constant, if you multiply by 0, it is 0. So we're not doing that. And the sum of a series of a sum is a sum of the series. And if both of them diverges, one of them converges and the other one diverges, or both, meaning at least one of them is divergent, then the whole thing is divergent. So it exists only if both of them exist. That's what it is. Right. Then it says that if we have positive integers, the series may start from m, may start from 1. It doesn't matter. They both converge or diverge, meaning that where there a series converge, does not depend on the finite number of terms added or removed from the series. So if we have the whole infinite series, taking the first few terms or adding the first few terms to it does not change much. Does not change the convergent and divergent of the series. What it changed, it just changed the values. The values of the series does change. Yeah, but convergent still convergent. If we take out a few terms or adding a few terms to it, the values will be different if it is convergent. That's essentially what it is. We will see one example like this. Right. Next, we go to geometric series. Remember, what we learned in previous section is geometric sequence of terms. This one we're talking about the series. Right. We have similar things though. Let R be the number if R absolute values R is less than 1, and we just mentioned before, this one is the same thing as R is between -1 and 1. And if it is the case, then the sum of the geometric series is equal to that. Notice that in order for the formula to work, this has to start from 0. And if our absolute value are greater than or equal to 1, then the series diverges. Right. So, like that. Whether we have the constant in front or not doesn't matter about the convergent or divergent. But in general, that is the formula. So of course, I think you see this in pre-calculus already. So between -1 and 1, not including, is convergent. Everything outside is divergent. Right. Now find the sum. First thing when we look at this, if we need to check is the ratio between -1 and 1. The ratio is 1/3. It certainly is. And we will check is the ratio between -1 and 1, and it's 1/3. So yes, if this is the case, then the sum, it does start from 0, which is good. Have to start from 0. So we say this the formula is A over 1 minus R. R is 1/3 and A is equal to 2. So we're going to have 2 over 1 minus 1/3. 1 minus 1/3 is 2/3. Divide fraction is multiply reciprocal. So we have 3. Right, so simple enough. Just need to check to make sure the ratio is between -1 and 1. If it is not, then diverges. The series diverges. Right, so simple enough. Right, that is a geometric series. We have a few more examples here. 3 more. Right. So just make sure that it has in the right form. The geometric series has to start from 0 and goes to infinity. May have a ratio, the constant, but most important the ratio, and that equal to A over 1 minus R only if R is less than 1 between -1 and 1. Right. So when we look at this, it will be easier if we rewrite this as take the -2 outside, right? Alright, like that. And then here we can say 1 raised to any power is still 1, and since both of them raised to the same power of k, you can bring that inside the power. Now in this one, obviously A is equal to -2 and R is equal to 1/5, and we do the check. Is that between -1 and 1? And 1/5 certainly is. So in that case, the series equal to is A over 1 minus R. A is -2. Over 1 minus 1/5. 1 minus 1/5 is 4/5. Multiply reciprocal. -2 and 4 cancel out. We have -5/2. Right. So simple enough. Right. Just make sure it is in the right form. Has to be start from 0 and has to be power of k. If it's not, just make some minor adjustment. Right. Next we have that. Now the power has to be k though, right? The form has to be exactly like that. And it starts from 0, at least we have that. Right. Now we try to keep everything in the k power, right? So here, if we want to split, we can say 3 to the first times 3 to the k. Because when we multiply the same thing, we add the exponents. 1 plus k give us that. Now, since both of this under the power of k, so we bring that inside the power of k. We have 1/3 still, and then we have negative 5 over 3 k. Right, for this one, the first term is 1/3. I'm sorry, not the first term, since the coefficient is 1/3. R is negative 5 over 3, right? Yeah, because that's exactly the form of the geometric series. Now, is the ratio between negative 1 and 1? That's negative 5/3, and so the answer is no. So if that is the case, then the sum does not exist. So in this case, we say the series diverges. Right? So simple enough. Yeah, just have the right form, that should be good. Right, next, this one though, it's not in the right form. Yeah. So the question answers find the sum if it exists. So all of this, if it exists, we find the sum. Of course, if it is divergent, the sum does not exist. Right, now, in order to use the formula, at least it has in the right form. So which is not. So k is not equal to 0. So if we want it to be 0, what do? If we want this to be 0, let's start. We start with, let me use this color, k equal to 1, right? If we want it to turn to 0, we subtract 0 on both sides. Of course, never do that, sorry. Subtract 1 on both sides. Subtract 0 to give us the same thing. So in that case, we have k minus 1 equal to 0. Now, if we want that to be 0, then k minus 1 equal to 0. And we're going to let n equal to that. So n is, we start from 0. And that is what we let n equal to. Yeah. So subtract 1 on both sides, give us 0. So n will start from 0 and increasing. Now, if n equal to k minus 1, so if we want to solve for k equal to what? N minus 1. Sorry, plus 1 on both sides and plus 1. So if we would substitute n plus 1 in here to all of the k's, let's see what we get. So the summation. Right. K equal to n plus 1. So I'm going to substitute n plus 1 into k. K is n plus 1. K is n plus 1. And k is n plus 1. So pretty much we substitute n plus 1 in all of the case. Because that's what we have here, right? K, and k. So that's what we have. Now, n plus 1 equal to 1. Subtract 1 on both sides. So that we have n equal to 0, which is good. We want the sum start from 0. And then here we have 5 times 2/3 n plus 1. And n plus 1 minus 1, that gives us 2 to the n. And then the bottom is 7 to the n plus 1. So at least we start from 0, which is good. Now what we do is we can split the sum in 2. Yeah, just split the sum in two. Now, just need to turn this in the right form, meaning the index start from 0 and the power is just be whatever that index is. So we're going to split. This is to the n plus 1, is meaning start to the first power, then to the n power. Because when we multiply, combine the powers, give us n plus 1. And then we have 2 to the n on the top. And then at the bottom, 7 to the first and 7 to the n. Right? So n plus 1 just split into 7 to the first and then 7 to the n. And then we can bring both of this into n power. I will multiply all of this. 2/3 to the first power is 2/3 times 5, 5 times 2, so we have 10 over 3. And then 2/3 n. And then we take out the 2 to the n and 7 to the n, bring them together. We still have 1 over 7. 2 and 7 to the n power. Now, the ratios, they are equal to 2/3 and equal to 2/7, and both of them between -1 and 1, which is good. That means we can use the formula here. So r equal to 2/3 is that between -1 and 1, and that is, and then r equal to 2 over 7, also between -1 and 1. So that's good. That's good. Right. Now, if it is the right form, we can use the formula that. So we have the first term over 1 minus the ratio minus the first term over 1 minus the ratio. Right, and then we'll just simplify. It's not the problem here, right? Just get the right form and we can simplify. It's not the point, that's just it's a calculation. That should be simple. Right. Now, next, you probably see this in the calculus or coarse algebra. We have the repeating decimal, and we're going to write that as fraction and use a geometric series while we're doing that. Right. Now, so when we write this, that is repeating decimal, we can say is 0.3 plus 0.03 plus 0.003 right. So one important thing that we didn't write out is the geometric series itself. If we start with a geometric series when k equal to 0 to infinity. So first we start this series by going to put 0 in for k, and that is essentially what we have, right? Or if we factor it out, there's a and r to 0 power is 1, and then just keep going to the end and then going on. So it's just the sum of all the powers. Right? We can do the same thing here. If we factor out 3, we have 0.1. But that doesn't sound to work, right? Remember, in this series, it starts from 1. So we have to factor out. In this case, it doesn't really helpful. What we actually want to factor out is something that we will have 1 on the first one. So that's good. Next, it's going to be 0.1. And then 0.01, 0.001, and then so on. So that's exactly what we want. So exactly as the sequence, as the series goes. Right? Now, how did that help? So according to this form of the geometric series, we're going to have 1 r squared and r to the n. So if this is r1, this is 1 r squared, r cubed, and then so on. So because of that, r is 0.1 and a is 0.3. So we have the series a r to the k equal to 0 to infinity. If we put in the numbers, this is going to be 0.3 times 0.1 to the k as k equal to 0 to infinity. Now the ratio is between -1 and 1, so that's good. So just say -1, 0.1, which is the ratio, and that check. So yes, so we just use the ratio and we say it's going to be a over 1 minus r, 0.3, 1 minus 0.1, so 0.3 over 0.9, 0.3 over 0.9 cancel out. That become 3 over 9. Just move decimal place 1 to the right, and we have 1/3. Of course, the calculator can also do that too if we just hit calculator is frozen, so let me restart it. If we just had 0.3 repeating, it does convert to fraction nicely, of course, but we're not doing that. A little more advanced here for next one. So 1.23 repeating decimal is 1 plus 0.232323. So if we split, and we can write like that. Now, notice we try to find one here does not have anything in common with the rest of this, so the one stay out of it. The rest we're going to need 1 r squared, r cubed, and so on in the geometric sequence, geometric series. So we're going to factor out 0.23 to have 1. Now if you factor that out, what is the next one? So we're going to set 0.0023 divided by 0.23, and we have 0.01. And then the next one we do the same thing. We have and then we just match. This is A1 R square and so on. So in this case R is 0.1 and A is 0.23. So we're going to have the 1 and then the summation of 0.23 times 0.01 to the k power, where k goes from 0 to infinity. Yeah, so just write that summation and make sure it is in the form of the geometric series. Yeah, in that form. So this is 1, and then here we just use the formula A over 1 minus R and subtract that, we have 0.99. By the way, the 0.01, that ratio is certainly between 1 and -1, so that check. And move the decimal place to the right, we have 1 plus 23 over 99. 1 plus 23 over 99. Of course we have that numbers, but we convert to fraction, and we have 122 over 99. Right, so that geometric series given in this form. Since it goes a little faster than I anticipated, so I just want to prove this formula real quick. It's not in the note, but I just want to prove this. Right, so we're trying to prove this formula here. So in order to prove that formula, we have to do just the basic. Let's say we just have A1 plus R square all the way to R to the n minus 1. I say we just do that. What's that equal to? By the way, the reason we stop at n minus 1 because when we multiply them out, this is the sum of the first n term. If we count 1, 2, 3, 4, 5 up to the n minus 1, there will be n terms. So that's what we have, right? Now, of course, we can also write A plus AR square, AR cubed, and all the way to the n term of AR n minus 1. So that's good. Now what we do is, we do this little trick and we multiply by -r. And you say, why do we do that? And I said, because it works. So now I just multiply -r into that sum. By the way, this point will bring nicely to the next part of the section, though, the telescoping series. Right, so multiply everything by -r. We have -AR square, -AR cubed, and still keep subtracting, all of them are negative. The last one is AR to the n, because when you multiply -r in here, that turns to negative, and r times r to n minus 1 is r to the n. Right. Now what we do is we add side by side. Just keep doing that. Here we have s to the n minus r times s to the n. If I factor it out, I have 1 minus r s to the n. Just factor out s to the n. And then when we add on the left hand side, what do we have? That cancel. That cancel. That cancel. And pretty much this will cancel with whatever in front of this. So what's left is a and negative a to the r to the n power. course, we can factor out the a. And with that, we have the partial sum of geometric series is divide this over. We have a 1 to the r to the n power over 1 minus r, which is perfectly, it's good, right? Now, the only thing we need is the ratio has to be between -1 and 1. So the ratio has to be between -1 and 1. Because of that, if we have a number between -1 and 1, so now this brings back to the geometric sequence. For the sequence, if r is between -1 and 1, that goes to 0, right? If we have a number like 1/2 raised to the n power, that goes to 0, right? So because that goes to 0, as n goes to infinity, so when we take this sum and goes to infinity, we do not have this anymore. We just have a on the top and 1 minus r. So that's all we have. And of course, it only works if r is between -1 and 1. So this little proof here is the proof for the geometric series. And of course, it has to be between -1 and 1 for the ratio. Right, so that geometric series. Now the next part is the telescoping series. Actually, this is very nice, and if we understand it, that's actually kind of a unique type of problem. Right, I'll get back to this because relatively this one is a little more complicated than the other two. I'm going to do this example first, and then we'll get back to that. Right, we actually did this, I think, in one of the sections, but yeah, I'll look it up later. Now we're going to write this. That looks like a problem that we can do partial fraction. So let's do the partial fraction. Split this up, see what happens. Right. So what I do is do the partial fraction of that. By the way, this problem might be long, so I just fold the page in half. So partial fraction, we have 1 over k plus 1. We can write this as 1 over k and k plus 1. I'll multiply both sides by the common denominator of k plus 1. Multiply it out. The top here is we have 1. By the way, we don't know if this is the case, so the coefficient have to be a and b, where we will solve for a and b. Sorry, should be that. Right, k and k cancel out. We have a, k plus 1, and cancel the k plus 1. We have bk. Now, this is simple enough. I will choose 2 values for k because there are 2 coefficients. So we choose something to make one of them disappear. So if we choose k equal to 0, this term gone. When k equal to 0, what do we have? 1 equal to a, 0 plus 1. So that gives us 1 equal to a. So we don't have to multiply now, combine like terms and solve the system equation. If it is simple like this. Now choose -1 because that will make the a disappear. 1 equal to a -1 plus 1 plus b times -1. When we simplify everything, that one cancel out. We have 1 equal to -b. So in that case, b is equal to -1. So we can say 1 over k times k plus 1 is equal to A is 1 and B is negative 1. So I'm going to write, instead of plus negative 1, I can put the negative 1 there. Right, so that's good. Right. Yeah, I need more space, so there's more than half of the page here, which is fine. Right, so we have that series can be split in two. By the way, it starts from 1 here, because if it starts from 0, it will be undefined. Right? Cannot divide by 0. So that's why it makes sense we start from 1. And some in the geometric series though, it starts from 0. Usually by default we let k go to 1, but in some cases it could be 0. Right. So instead of writing that, we're going to write this: 1 over k minus 1 over k plus 1. Right. So that's nice and all, but how did that help us? Notice that we can write this out, and this is not any, it's not in the geometric series. That at least we know it's not. So what can we do here? So why don't we just write out a bunch of terms and see what happened? Let k equal to 1 and put 1 in here. Next, put 2 in there. And then put 3 in there. And let's say all the way to, if we put n in there, we have 1 over n minus 1 over n plus 1. And we're not stopping there, we just keep going. Right. Now let's just rewrite this without the parentheses. 1 minus 1 half plus 1 half minus 1 third plus 1 third minus 1 fourth. And then we have 1 over n minus 1 over n plus 1. Now, of course, there are a lot to cancel. This, and then pretty much everything we cancel here. We're left with that term. Of course, this can go on to infinity though. So we say, if we stop at that term, we're going to have this. So that series is equal to this. Of course, at n goes to infinity though. Right? Now, of course, when n goes to infinity, that just cancels out. And whenever we stop, we have 1 first, and then whatever at the last one. So now, we say, as n goes to infinity, that one goes to 0, right? Simply because we have 1 on the top, infinity on the top, finite on the top, infinity at the bottom. So that's why it goes to 0. Of course, we see plenty of that. We saw plenty of that already. Right. So if that one go to 0, this sum is that one go to 0, and we just have 1, right? So that go to 0, so that it's just 1. So the summation equal to 1, because that one goes to 0. and this one goes to 1 because this one goes to 0. Right. So now that's nice and all, but just want to do this one again, but just using some visualization, because this will help you to do some of the homework problem, because it's not always cancel the next one nicely like this. Right. But here's my attempt. So let's say we have the dominoes, because domino we have 1 and a 2. I'll write 1 in different color like that in purpose. And then the next one we have dominoes of 2 and a 3. So just like what we have. The first one is the plus, the second one is the minus. And I'm just put the dominoes back to back. And then let's just keep doing that, and let's see that at the end dominoes we're going to have n and n plus 1, and because the domino keep on going as this is an infinite series. Right. Now when we link up the dominoes, those two link up, the 3 link up, the 4, and then all the everything link up. What is not linked is the first term, so we're going to have 1 here. And if this the way it works, everything in the middle will cancel out except the n plus 1 will be at, if we stop here, that's what we have. And because of the n plus 1 here corresponding to minus, so we have 1, the first one, and then n plus 1. So the first and the very last, everything in the middle cancel out. So that's what the telescoping series does. Right. In this case, that go to 1. It's nice. Right. So try to think about something like this, because the next one is not quite the same. Right. We still have number 3 here, but let's do this one first. Right. So let's look at this. It will be useful if we write out the first few terms. Right, let's write out the first few terms. What happens when k equal to 1? Put 1 here. 1 over 3 to the first minus 1. Put 1 here. 1 plus 2, 3. Now put 2 in for k. Two plus 2 is 4. And now put 3 in. I'm sorry. I'm going to do one more. And the characteristic, put 4 in, that's what we have. A characteristic of telescoping series is within this cell a term there's a positive and a negative, but they cannot always link up back to back like this. But if we keep going, we're going to put n in for k. And keep going on to infinity. Right. Now let's write out 1/3 minus 1 3 cubed plus 1 over 3 squared minus 1 over 3 to the 4th plus 1 over 3 cubed minus 1 3/5 plus 1 to 3/4 minus 1 over 3/6. In fact, instead go put n here, I put n minus 1 in there as well. So if we put n minus 1, we have 1 over 3 n minus 1. Put here n minus 1, n minus 1 here, give us n plus 1. And then that term. So I'm going to wedge terms in here. Let's put, if you put n minus 1 there, yeah, I'm going to add one more term by putting n minus 1 into k. So we have that term before this. That's always 1 plus 1 minus. Right, now let's cancel. Negative 1/3. What else get cancelled to? Oh, here. That does that cancel to anything? Nope. Right, this one though. This one cancel with something. This and minus, yeah, there will be something there. So this will be cancelled with something in the middle here. So when we cancel out, what term actually left? Yeah, kind of difficult when we look like this, right? So let's look in terms of the dominoes that we had before. But this domino, they don't have consecutive terms like this. What they have is, instead of 1 and 2, 2 and 3, 3 and 4, they skip one term, 1 and then 3, 2 and 4, 3 and 5. So let's write the domino like that. So let's just close this out. Now the domino will be like this. Sorry, just want to write a bunch of dominoes. So like I said, one of them is positive, the other one is negative. Right. See this one, when we put n in there, it's going to be n plus 1. And here, if we put n minus 1, sorry, skip, so the n plus 2, and this is n plus 1. So this is n plus 1. Let's make it a little bit bigger. Right. So we're going to stop at n, and this will be n plus 2. And the term before that is n minus 1. Plus 2 to that is n plus 1. Now let's link up the 3 here. We'll link with this 3. The 1 here doesn't link to anything. The 2 here doesn't link to anything. The 4 will link to this 4. The 5 link to this 5. And the 6 will link to something. Just keep rolling. So what we see here is, look like everything in the middle cancel out, but we left 2 of the blue in front, 2 of the positives in front. If we have that, so just like domino, everything have to be in balance. If we want to take one positive, think about this. If you take out all the dominoes, one blue, one red. If you take out a red and a blue, a red and a blue, a red and a blue, always we have at the end one blue and one red. Same thing here. If we took out everything in the middle, there are two blues from the beginning. Then we have to be two red on the back, because whatever blue we have the same number of red at the bottom. Because every time we link up one red, take out one blue, one plus, take out the minus, pretty much. So if we have two plus from the beginning, there should be two minus on the back. So because of that, what we meant here is where we have 1 and where we have 2, and then we have the n plus 1 and the n plus 2. Yeah, to keep things balanced. That's why I write this in terms of the dominoes. Right, so after all of that, there's 2 plus in the beginning, 2 pluses, and in that case there will be 2 minus on the back. And so that means this one and this one. Now, if it is like this, as n go to infinity, that go to 0, because finite divided by infinity, finite divided by infinity, that go to 0. We're left with this. So we say as n goes to infinity, usually they say we have k, but let's say if we stop at n, so we can say this is equal to s of n. I mean, that is the bad way to write it, because this one potentially keep going. So we will say here, if we stop at n, we're going to have 1 over 3 square, 3n plus 1, n plus 2. Right, so that is the partial sum. If we go from 1 to n, yeah, cancel everything in the middle, 2 plus from the beginning, there will be 2 minus on the back to balance it, because every time we link, we take out one positive and one negative. So the number positive and the number positive and the number negative, those numbers have to be the same. So that's why we end up with this. Now, if we take n goes to infinity, the sum of the sequence, as n goes to infinity, we're just going to take the limit of this. Notice that this is a series, this is not a sum. This is not a sequence. A series is the sum of every terms in the sequence, not a particular term, but the sum of all those terms. And that n goes to infinity, that goes to 0, that goes to 0, because as we said before, finite divided by infinity is 0. So we have 1 over 3 plus 1 over 9. So whatever that is. Right, 4 over 9. So that's nice, right? So that's why I write this in the term of the domino, so we can visualize this. Right, still have one problem. So the telescopic series, each term itself is a positive and a negative. So we don't have that yet, but actually this turned out to be very simple. We have ln of the quotient is the difference of the ln. So when we write like that, yes, we have a sum. So this one we can split that as ln of k plus 1 minus ln k. Now it will make more sense, easier to reasoning if we just put the numbers in. If we put 1 in for k, 1 plus 1, 2, put 1 in there. ln of 1 is 0, but worry about that later. So the next one, I'm going to put 2 in there. Then put 3 in there. How about we put n in there? And that series continue. So this actually, when we put up to n, this is the partial sum s of n. So the sum of the first n terms. Right. So let's now, what is the sum of the first n term? Now let's write this out without the bracket. L2 minus ln of 1, which is 0. Yeah, I'm just gonna say, right. ln of 3 minus ln of 2, ln of 4 minus ln of 3, ln of n plus 1 minus ln of n. Now let's simplify. That cancel out. That cancel out. Does that cancel out? Answer will be yes. The next one will be 5 and minus 4. The minus 4 cancel with this. So when we cancel out, notice that we left with the minus from the beginning. So that's why we're going to need the plus 1 on the back to cancel out. Remember, each term has a plus and a minus. Every time we cancel out, we take our plus, we take our minus. So the number of pluses and the number of minuses have to be the same. So after everything cancel out, since we have remaining 1 minus from the beginning, we're going to need 1 plus on the back. So that's why we're going to need this term. And so just ln of n plus 1 minus 0, really. So minus 0 plus ln of n plus 1. So that is s of n. So as, how do we write that? So the series as n goes to infinity of s of n, we're going to take the limit of this. And we have ln of infinity, which is infinity. So because of that, this series diverges. So, yeah, think about the telescoping series of a positive and a negative in the big scheme of things. So, we not always we can cancel everything, grip with the first and the last. It's not always like that. Sometimes we have a few terms on the beginning. In that case, we have a few terms on the back. But the number of pluses and the number of minuses, they have to be the same. So if we write the dominoes for this problem, Remember, we start with a plus 1 is a 2, and then 1, 3, and a 2, 4, and a 3, 5, and a 4. So number going backward like that. And so if we stop at n, where do we stop at? When we put k equal to n into the expression, so we're going to add n plus 1 and then n. Now let's link the dominoes. The 1 here doesn't link to anything, the 2 does. Yep. And then the 3, the 4th. Now, and the 5 here will cancel out. So everything clear out. We have 1 minus from the beginning. So we have to left with 1 plus on the back to keep things balanced. And that's why we end up with that. And ln, limit of ln of n as n go to infinity, ln of infinity is infinity. So that's why the series diverges. So that's the section. So in this section we learn about 2 things. First one is geometric series. The second one is the telescoping series. We did quite a few examples. For geometric series, all you need is that one. This is a series, so the sum of every term in the sequence is going to be that. Not the sequence. The sequence is the list of single term. The series is the sum of all those terms. And we have geometric series, so that formula. And the telescoping series, when we write the telescoping series, each term is going to have a plus and a minus in some certain type. Could be, may not be the consecutive terms, but we have to write out a few terms and then try to see what cancel, what remain, how many plus or minus from the beginning. We're going to need how many minus and plus on the back to keep things balanced. So that's what we have on the telescoping series. But with that, I'm going to stop a section right here because that's all I need to cover for this section. See you in another video. As always, thank you for watching.